In this example, we're asked to find the domain of the Bessel function of order 0. And what you notice here is that this function is defined as an infinite series with the variable x in the series here, right? So it's actually an infinite power series. And so the question is, for which values of x does this series converge? So what can we do to solve for the domain? Well, we can do what we did before and try and find for which values of x this series will satisfy the result of the ratio test that makes that ratio less than 1. So we'll do the same trick we did in the previous example with the ratio test. We know that when we take the limit as n goes to infinity of the absolute value of an plus 1 over an, and this comes out to be something that's less than 1 in absolute value, then we know by the ratio test that it will be convergent. So we want to find all values of x such that this satisfies that conclusion of the ratio test. Okay, so let's try and write it out here. Now notice this one's a little bit more complicated than the last series, but the goal here will be to replace n with n plus 1 to get an plus 1. So everywhere I see an n, I'm going to replace it with n plus 1. Notice here I'm grouping it. Right, we have 2 times parentheses n plus 1 in the power here and here. And then down here we're going to have n plus 1 in parentheses factorial, and then that whole thing squared. Okay, so that was just putting in n plus 1 everywhere I see an n. And then we'll multiply by the reciprocal of the nth term here. Okay, now we can try and simplify. Okay, so before I simplify, let's remove what we can here. So the negative 1 to the n plus 1, those factors will go away because of the absolute values. They make any negative constants positive, so the negative 1 to the n factors will just become positive. And now I can look at dividing some of these other terms. For instance, here 2 to the 2n plus 1, that's really 2 to the 2n plus 2 power. So when I divide out here the 2 to the 2n with that, it'll just divide out the 2n part. So here I'm going to be left with 2 squared in the denominator. And notice something similar happens here where I've got x to the 2n plus 1, so that'll be really x to the 2n plus 2. Let's scooch that over a little bit. So when I divide that with the x to the 2n plus 2, or x to the 2n here, the 2n divides. So I'm just left with x squared. Okay, so let's write what we have so far. We simplify these x factors and we're left with x squared in the top. We simplified the 2 factors and we're left with 2 squared in the bottom. We got rid of the negative 1 factors. What's left are these factorials. Remember here that n plus 1 factorial is the same as n plus 1 times n factorial, and then we're squaring it. So squaring each of these factors here, we can then divide out the n factorial squared here. So I'm left with n plus 1 squared in the denominator. Okay, so this simplifies quite a bit, and now this limit here as n goes to infinity will simply focus on this denominator part. Remember that x squared here is really constant with respect to this limit, so I can even pull that aside and just look at what happens to the limit as n approaches infinity of 1 over 2 squared, which is 4, times n plus 1 squared. And so, of course, here as n goes to infinity, n plus 1 squared goes to infinity, so this is 1 over something that approaches infinity, which is 0. Okay. And notice here, this will be 0 regardless of what value of x we choose to plug in. And so, regardless of what value of x we have, this will always be less than 1. Therefore, it will always satisfy the conclusion that it'll be convergent. So in this case, it's absolutely convergent for all x. So it converges on the domain. It converges on the domain negative infinity to infinity, so all real numbers. So the domain of this Bessel function is the whole real line. Okay. So at this point, we've kind of seen a few different cases of how we can get the set of x's for which a power series converges. So what can happen in general is one of these three possibilities that we see here. So for any given power series, Cn x minus a to the n, there are three possible outcomes that could occur. The series could possibly converge only at the center, only at one value of x, which is always going to be the center. In fact, we notice that for any power series, if I plug in the center for x, you're always going to get 0, right? So we know that any power series will always converge at its center. So that's one possibility, is that it only converges at the center and diverges everywhere else. Another possibility is that the series converges for all x, which is the example that we just saw a moment ago. All right, we showed that that series converges for every value of x. Or, like the previous example, we saw that there was a specific interval for which it converges, and it'll diverge outside of that interval. And so we can look at that as there being some number r such that the series converges when the absolute value of x minus a is less than r, and diverges if the absolute value of x minus a is greater than r. So looking at the previous example where we showed that x minus 3 would be less than 1 when it converges. So this value that we're denoting with r here is called the radius of convergence. Okay, so in a way it tells us the width of the interval on which our series is convergent. Notice that by convention we'll say that if the series converges for all x, then we'll use the interval, or the radius of convergence will be infinity. And if it only converges at one value of x, then we'll use the radius of convergence is 0. Okay, so in this case that would make sense, because here if I'm converging only at a single point, then the interval on which it's converging has no width. Right, it's just a single point. So you can imagine that the interval that contains just the point A has no width to it. And here it makes sense that if I have the interval of all real numbers, well, it contains everything. So it's everything greater than A and everything less than A. Whereas this interval here that it converges will only contain those values that are a distance r away from A. So A plus r, A minus r over here, and so it just converges for those values in between. And so it makes sense here that the width of that interval is given by the radius of convergence r. And The interval on which it's converging we'll call the interval of convergence. So this is the interval that contains all values of x for which the series converges. So we saw in a couple cases when it converges at a single point that in fact it's not an interval, it's just a single point. Or if it converges for every value of x, then the interval of convergence would be all real numbers, the whole number line from negative to infinity. Or in the third case, when we saw that it only converges for values of x such that the absolute value of x minus a is less than r, well, we showed in our example that this really corresponds to some interval centered around a. Right, because here I can open it up. And so here we would look at the values that are in between a minus r and a plus r. And in our example that we looked at, we noticed that it's very possible that at the endpoints it could be convergent or it could be divergent. So we have different possibilities at the endpoints. They could be included or they could be not included. They could be open at the endpoints. Okay, so you could have variation of different possibilities. You could have closed at both ends, closed at one end, open at the other, or open at both ends. So remember, we have to test those endpoints in order to determine whether or not they're included in the interval of convergence. Here, let's walk through an example where we can practice finding the radius and interval of convergence. And I'll use the ratio test like we did before, because that provides a useful tool for breaking this down into an inequality statement at the end that we can try and solve. Okay, so we'll start with an plus 1 over an and see how that simplifies. So I'll have negative 3 to the n plus 1, x to the n plus 1, over n plus 1, so that'll be n plus 2 down here. And times the reciprocal, n plus 1 over negative 3 to the n, x to the n. And then let's see how this simplifies. Remember that here negative 3 to the n divides with negative 3 to the n up here. X to the n divides with x to the n up here. And then here I'll put these square roots together. And then I'm left with the absolute value of negative 3 is really just the positive 3 times the absolute value of x. Notice I leave the absolute values around the x because x is a variable here. And then as I take n to infinity, this part here is going to approach 1. One way I could see that is actually here, let's walk through the steps of why that's the case. I can bring the limit inside of the square root. And this simplifies to 1 plus 1 over n, and then 1 plus 2 over n, which that approaches 1. So now we see that this has to approach 1. So we have 1 times 3 absolute value of x, leaves me with 3 times the absolute value of x. And we want to say that that's less than 1 in order for it to be convergent. So now we have the absolute value of x is going to be less than 1/3 when it's convergent. Okay, so now you see it's in this form. Absolute value of x minus a is less than r, right? And so here, 1/3 is our radius of convergence. Okay, now to get the interval of convergence, right, so actually here, let me write that down here. R is 1/3. So radius of convergence. Now to get our interval of convergence, let's open up that inequality. Absolute value of x is less than 1/3. Gives me that x is between -1/3 and +1/3. And now I'm going to check the endpoints. To see whether or not -1/3 or +1/3 are included in the interval. So at x equals -1/3, when I substitute that in for x here, I get -3 to the n times -1/3 to the n over the square root of n plus 1. Notice here that these guys simplify. -3 to the n times -1/3 to the n just becomes 1 to the n, which is just 1. So this simplifies to the series 1 over the square root of n plus 1. And when this started with n equals 0, but I can re-index here. So here's a little trick, is if I re-index this to start with n equals 1, notice that the first term would be 1 over the square root of 0 plus 1. So if I re-index it to start at n equals 1, then it's just this 1 over the square root of n, and we see that this is a divergent p-series. So it'll be divergent when x equals -1/3. So we see that this one is not included in our interval of convergence. Let's test the other endpoint. At x equals +1/3. So here we get the series -3 to the n times +1/3 to the n, the square root of n plus 1. Here when I multiply -3 times 1/3, we get -1. So this will be -1 to the n over the square root of n plus 1. Now this is an alternating series. And you see that as n goes to infinity, 1 over the square root of n plus 1 goes to 0 as n goes to infinity, so it's convergent by alternating series test. Okay, so we've shown that it is convergent here at x equals 1/3, but it wasn't at -1/3. So we're going to make sure that we include x equals +1/3, but not x equals -1/3. Okay, so with that we can say our interval of convergence here contains -1/3 to +1/3, where it's open at -1/3 and closed at +1/3.